So we finally get to talk about hypothesis testing. The last little section that we are talking about here is, of course, with a mean, but this time, what happens if you don't know sigma? Now, I want to remind you that if you did know sigma, what type of test would you use? A z-test. What happens if you don't know sigma? You're going to use a... Yeah, so it all comes down to, again, just like Chapter 7, very, very similar order of steps that we took here. First it was proportions, then it was mean knowing sigma, now it's mean not knowing sigma, z, z, t. Okay, so pretty much it's up to you to know the difference between a proportion and a mean. Proportions are z's. Means, you have two options. You have you know sigma, z, you don't know sigma, t. You got it? So same exact idea that we've been dealing with. Of course our requirements are pretty similar. We still need the requirement for a random sample. Of course that's going to almost go without saying. You have to have random samples, otherwise you bias your data. Requirement 2 is, it's weird to have a requirement, but your sigma shouldn't be known. If your sigma was known, if your population standard deviation was known, you wouldn't even be doing this. You'd be in the last section. You'd be in section 8.4, right? Because you know sigma, all the requirements would be met. You'd be using a z-test statistic and a z critical value. Here we go, okay, well, if we don't know our sigma, sigma stands for population standard deviation. So on your wording of your problems, instead of saying population standard deviation is, it's going to say sample standard deviation is. Are you with me? You've got to have a standard deviation somewhere. You're going to have a standard deviation. It's just you have to read very carefully whether it says population standard deviation, i.e. a z-score, or sample standard deviation, what we're learning today. So sigma is not known. But S is. Lastly, what was that magic number again? N was the sample size has to be what now? 4? What is normally distributed? The population. That's right. So either your sample size is more than 30, in which case it will fit a standard normal curve, or a normal distribution, or your population has to be normally distributed, because if you sample from that, you'll get another normal distribution when you consider your central limit theorem. So n's more than 30, or the population is normal. If these are the cases, if we don't know sigma, but we do know S, and everything else is the same as last section, then we're not going to have a z-test statistic anymore. Our test statistic is going to be a t. Now, fortunately for us, we've already calculated this. We should know how to do it. It's not too bad. It looks very similar to our z-test statistic. It still has x bar. And what's x bar stand for again? Sample mean. Okay, good, because we're still basing our evidence and getting our claim on our evidence compared to our population guess, pretty much, with our null hypothesis. So it's our evidence. We subtract the actual claim from it, what we're trying to state about our population mean. And we're seeing if this is rare enough to void our null hypothesis, basically. Now, down here, what goes here? Yeah, standard deviation. Typically, it would be sigma for a z-score, right? But we don't have a z-test statistic here. We have a t. So we're not going to know sigma, so we got to use the different letter that's like S. And here's the same thing, square root of n. The steps are literally identical to section 8.3 and 8.4. You're going to do the same 7 steps. First is going to come your claim, then your null and your alternative, then your significance level, then your test statistic. After that, though, we only have one option. You're not going to be using the p-value method here, which is why I taught you the traditional method to begin with. Because in a t-value, or a t-test statistic test, it's really hard to find out the p-value. Right, you need a calculator to do it. You can approximate with your table, but if you look at your table only works one way. Your table only works on giving you the area, or the critical values, based on the amount of significance in each tail. Have you noticed that? It only works one way. It's not like a z-score that works both ways. So your calculator would do it. Your calculator would do it. And I could show you that if you'd like to learn it. But since everyone doesn't have a graphic calculator, I can't make you learn a p-value test because you wouldn't even be able to do it for half of you. You follow? Since it's not a requirement for this course, I'm not going to teach you the p-value method. I'm going to teach you the traditional method for solving this with a t-test statistic. Do you understand? Okay, so there's only the traditional method for us. Traditional method only. Let's do this with an example. We'll work our way through all 7 steps, figure out if we can apply the last information to this section. So let's say that, excuse me, that you're in the business of bottling soda. Now, of course, we want to make sure that how many ounces are in a can of soda typically?
12.
About 12 ounces, that's right. Now, are you going to be exactly at 12 ounces every time you make a soda? Nah, you can be a little less, a little more. But you want to be really, really close to 12, right? So let's say that you're on the line and you're in charge of quality control. And so these quality control people, they typically will take a sample. They're not going to check every soda. You can't do that. But they'll pull off a couple hundred sodas, open them up, and sneeze right in and put it back. No, just kidding. They'll open them all up, they'll dump them out, and they'll figure out how much soda was in each can. It should be right about 12 ounces. True? You don't want too little, you don't want too much. So this guy has collected all these sodas, he's dumped them out, and he's found out that the average level of soda is right around 12.11 ounces. That's more than they should have, right? So he's going to go and say, well, let's see. I want to test this claim to see whether or not we're actually giving away too much soda consistently. Now, of course, that sample had too much soda in it on average, right? But he needs to be sure enough. It needs to be significantly more for him to say, hey, we need to recheck our production. Because it could have been this. It could have been that how much did he have to say? He pulled off 39 sodas. It could be that the 39 sodas he pulled off just happened to be the ones that were a little bit fuller every single time. You with me? That's going to happen. That's going to be the random chance. That's why it's that sample. There's some randomness to that. It's not every soda he's considering. So we need to find out, is his sample significantly different enough from the 12 ounces to state with a certain measure of certainty that we are producing cans with too much soda in it. You guys understand the idea here? So is it producing too much soda? Well, for those 39 cans, yes. But is that significantly different enough to say that it's for everything to a certain level of significance? In our case, it would be 0.01. So let's try to go ahead and do this problem. So you're in the soda business. You sample 39 cans of soda. The mean volume of soda was 12.11 ounces. With a sample standard deviation of 0.27 ounces. What I want to do is test this guy's claim, because this guy said, well, wait a second, I know that this is more than what we should have, 12 ounces. So I'm going to test the claim that we are producing too much soda. So test the claim that the mean level of soda, mean volume of soda, is more than 12 ounces, what the volume that should be in a can. Firstly, does the wording look familiar? Should look a lot like your homework looked. It's going to read exactly like a test problem is going to read. This is going to be a test problem, or something really, really similar, worded exactly the same way. So we have a sample of a certain number of things. You have a mean of whatever it is with a standard sample standard deviation of something, and then it's going to say test the claim that, and it's going to give you some population parameter that you're going to test here based on some evidence that you collected. First, I want to go back just a little bit. Do you understand that we've actually done the work necessary to collect a sample like this? If I gave you 39 cans and said, here's the level of the soda in there, 12.0, 12.05, 11.99. I gave you 39 of those. Would you be able to calculate the mean? Yeah, you could actually do that, right? Would you be able to calculate standard deviation? Sure, you plug in your calculator, you could do that, plus I gave you formulas. So you have the ability to find this, well you can count, this, where you can do the mean, and this, where you can do the standard deviation. You have the ability to actually do that. Now we don't do it because it takes a long time to do that stuff, right? That was in your first test. But you could actually do that. Next up, I want to refresh your memory on significance level. Our significance level is 0.01 here. So when we're talking about a 0.01 significance level, it's saying we're a certain amount, we have a level of certainty about our result here. How certain are we going to be when we're done with this that we're correct? 99% certain. That's right. If I made that 0.05, we'd only be 95% certain. You guys okay with that one? All right. By the way, if I have a 0.02, how certain am I going to be? 98%. Yeah, we can also use that one on the t-test. It's pretty easy to find that one. It's one of our columns. Okay. Now, in order to do our problem, we have to get this categorized correctly. So, first thing we do is identify whether we're talking about a proportion or a mean. Which are we talking about here? Clearly a mean. I'm even in the correct section for means. But I want you to really read through that and understand it. So it says nothing about proportion. We see here we're talking about means, mean volume, test a claim that the mean, that's really where we're getting it, is what our claim says. It's not about proportion. It's not saying most or more or something like that. That would be proportion words. This says that the mean. So we're definitely talking about mu here. It's a population mean. Next thing within our means, we've got to categorize whether we're talking about a z-test statistic or a t-test statistic, and that's based on one thing and one thing only, whether or not you know the population standard deviation. Now I got to tell you, you're always going to have at least some standard deviation. It has to give it to you, otherwise this you can't do, right? A standard deviation goes there. You're going to have one of them. You just have to say whether you have a population or a sample standard deviation. It'll say explicitly on your paper, either population, or assume population standard deviation is, or population standard deviation is this. If it says anything else, if it says you have a sample with a mean of this and a standard deviation of, it's implied that that sample standard deviation is what that number is. All right, here I'm going to say it even more explicitly for you, with a sample standard deviation of this. Do we know sigma or do we know S? We know S, because it said sample standard deviation. That's the key thing that's going to happen on your test, because of course I'm not going to say this problem is from 8.4, this problem is from 8.5, and that way you know. You actually have to read it and understand what these things are saying. So sample standard deviation says we don't even know sigma, we know S. Now, let's go back and do our steps one by one. Step number one is you're supposed to make up a claim. Now, you used to be pretty proficient at doing those steps because you had to do a lot of steps last homework. So we want to state our claim. And the opposite of the claim. You guys are going to be so good at hypothesis testing. Yeah! What's our claim?
Mu is greater than 12.
Definitely mu, not p, right? I'm not talking about proportion, definitely mu. Greater than is this one or this one? Which one? That or that?
That.
That's greater than. So the equal, that's important, right? Because that dictates where our null hypothesis is. That's a big thing. We have to get that right. So mu is greater than 12. When it says test the claim, that's where we're getting our claim. Greater than 12 ounces. Of course, the opposite is just really flipping that sign around and putting the equal somewhere. So we'd have mu, we would have 12 less than or equal to is the opposite statement than greater than. Which one of these things is going to be our h sub 0, the top or the bottom?
Bottom.
Wherever that equality is, that's our h sub 0. H sub 1 would therefore be our claim. Oh, let me ask you a critical thinking question. Are we going to be able to prove our claim correct in this situation?
Yes.
The only thing you can prove correct, if it works out for you, is h sub 1. If we prove h sub 1 correct, that means our claim is correct. You follow? That's why I said in order to actually prove a statement, you've got to somehow state it so that it's going to be h sub 1. H sub 0, you can't ever prove that right. You can only prove it wrong. Okay, so we got that. Let's look at step number 2. It's basically just a restatement of these things. But it's important because we replace the less than or equal to with an equality, and that gives us the information we need for our test statistic. So we'll want our h sub 0 first, then we'll want our h sub 1. H sub 0, tell me what I need to write.
Mean equals 12L.
Good, we replace this with an equal sign because our h sub 0 has to have an equals. That's telling us what this is going to be. We never change h sub 1 though. That's telling us what type of test we have, either a left tail, right tail, or a two-tail test. You okay with that so far? So first one, really important, not too hard, but really important step. Test number 3 is probably the easiest. Test number 3, you just give me alpha. It's 0.01. That stands for our significance level. And test number 4, notice how you do the same exact thing for every single type of problem we've had so far. Test number 4 is where you make your decision whether you're using a Z or a T. In our case, because we don't know our sigma, we know our S, we're going to be using a t-test statistic here. So the few things we need to know about a t-test statistic, we need to know x bar, S, mu, and N. So in our case, our t-test statistic, what is our x bar in our case, ladies and gentlemen? What's our x bar? Yeah, our x bar comes first. X bar is the evidence that's from our sample because that's our sample mean, so 12.11 is what we're looking at. Minus 12.11 minus. What is our mu? How much is our mu? Good, it comes from your h sub 0. That's why we stated that way. So you look back at your h sub 0, it says, oh, your mu, what this thing is, that's 12. That's what we're testing as our claim. So this is our evidence saying, is this far enough? Look at it. What this basically says is this far enough away from 12? Clearly it's bigger than 12, but is it big enough? Is it bigger enough? Is it big enough to a significant level, that's a significant level, to say that we are producing too much soda in these cans? That's the idea. Divided by, what is our S in this case? Why is it S and not sigma again?
Because it's sample.
Okay. Divided by the square root of, what's our square root? Divided by the square root of 39. Okay. Do the math for me, figure that thing out. That's something you guys are going to have to be able to do. Remember, you can do this as a way of getting around this whole division symbol thing. You can do 12.11 minus 12, you're going to get 0.11. Divide that by 0.27 and multiply by the square root of 39. It'll be the same exact thing. You should get 2 point something. 2 point what? 2.54. Okay, 2.54. Now, I also have to tell you that t-tables are typically to 3 digits. If you look at your t-table, aren't those to 3 digits? Get out your t-table for me. Do they give it to you to 3 digits? Point something, something, something?
Yeah.
Okay, so give me this to 3 digits, please. Okay, show of hands. How many people have calculators out there? Keep your hands up if you're able to find that. All right, that's good. That's fantastic. So our test statistic is 2.544. Now, in the previous sections we had two options. We had a p-value method, we had the traditional method. The p-value method would do this. Look at me. The p-value method would draw a picture, it would be a certain type of tail test, it would put this on there, right, and put that on there, and then would find the area associated with that value. However, if you look at your t-table right now, there's actually no way to do that. You look to see where this was, you look at your degrees of freedom, you look at your significance level, but it's very hard to do, right? There's not a 2.544 on your table there exactly what you have to have. So it's really kind of an approximation if you were to try to use your table and get a p-value here. Now, will your calculator do it? Yeah, your calculator will. You do an inverse t distribution, and that would give you use your t-distribution, that would give you the area in the tail here. So you can do it with the calculator. For us though, p-value methods would be real difficult because your table's not going to give it to you. So we just use the traditional. So for step number 5, there's no two options anymore. There's just this. Draw your picture like we're comfortable with, and tell me whether we're a left tail, a right tail, or a two-tail test and why. So we look here. This tells us where we're at. So this is kind of an important thing, right? This tells us two pieces of information. First, the mu for your test statistic. Also tells you a left tail, right tail, or two-tail test. This one's a right tail. So over here we'll go, okay, right tail test. Now the traditional method said you're supposed to do this. You're supposed to look your alpha up in some sort of table and give me a critical value. So we're going to be looking for a critical value here. That's what the traditional method was. Remember doing traditional method on your homework, right? Critical value. It will separate this into the fail to reject region and the reject region. Which one's the fail to reject region, left or right? So this is FTR, fail to reject. And that's my rejection region. Hey, what's the area in our tail? What's the area in our tail? You can don't. What is it? Yeah, the area in the tail is the value to which we're significant enough. It says, okay, if we're past that level, saying that's really, really rare, right? That says our rareness. That's what that is. It says if you're past the 0.01 marker, where there's only a 1% probability that you're over there, that's pretty darn rare. That's saying that your null hypothesis is probably incorrect if you're over here. If you're over here, well, you can't say that's not enough evidence. That tells you how rare you're supposed to be. So what we do is we use that how rare you're supposed to be, the significance level, to find a marker for that according to the t-value, which we're comparing it to. That's the whole idea. So here our tail was, yeah, you guys had it, 0.01. Where you get that is from your alpha. That's why we call the area in the tails alpha. That's our significance level is alpha. So it comes down to you got to be able to look up 0.01 in that table that I had you pull out in your t table, the t distribution, and figure out what your critical value is. You need to know a couple things about that, right? Firstly, you need to know whether we're talking about a one-tail or two-tail test. So I want you to look at the top of your table. And at the top of your table there, it says that. It breaks it down nice and neat for you. Do you see it? It says the area in one tail up at the top. It says the area in two tails down at the bottom. Then it gives you your degrees of freedom. Do you remember how to find your degrees of freedom? Yeah. What is your degrees of freedom here? So our degrees of freedom specifically is how much? 38. Do we have a 38 on here? If we don't have a 38, for instance, if you're more than 41, right, you're gonna have to go to just what's closest to, because there's not that much difference after about 40 or so. So we're gonna go to 38. That's the row that we're gonna be in. What column are we gonna be in? Well, let's take a look at that. Are we talking about a one-tail or a two-tail test? So we're gonna look up the one-tail. How much area was in our one-tail? How much?
2.429.
Oh, area in one tail?
Oh, 0.01.
0.01. Okay, very good. So area in one tail says 0.01. So we're going to go down there to all the way, let's see. Wait, you looked up 38, right? So we're down at 38. 2.4. Did you find the 2.429? All right. So we use our t-distribution to go ahead and look up our alpha, depending on whether a left tail or right tail test, and find a critical value that we're going to test our test statistic against. Would you raise your hand if you feel okay finding the 2.429? Great. Now is our decision time. Decision time says, okay, now you're going to look at that and you're going to actually test your test statistic. This is where you put this on the chart. Where does our test statistic fall? Does it fall in the fail to reject region or the reject region? Which one?
Reject.
Clearly reject region. It's 2.54. Here's 2.4. It's just slightly over there, but it is in the rejection region. Saying, okay, well, if we fall over here, am I going to reject h sub 0 or fail to reject h sub 0? We're in the rejection region, so we're going to reject. What does rejecting h sub 0 mean? Good. Now look at why this works again for the last time, okay? So if you reject h sub 0, that means you reject this statement, your null hypothesis. That means you accept h sub 1. Since h sub 1 was our claim, we just proved our claim. So rejecting h sub 0 automatically accepts h sub 1. If h sub 1 is your claim, which it will be if it's stated properly, if you rejected h sub 0, your claim is going to be proved right, basically. You're going to accept h sub 1. That proves our statement, and what we can say here is number 7. If you reject your h sub 0 and you accept your h sub 1, that means there is enough evidence to support the claim that, and then you restate whatever claim I have told you. That's exactly what I want to see on your test. I want to see 1, 2, 3, 4, 5, 6, 7, and step number 7 I want it written out. I want it, there is enough evidence, don't just say there is enough evidence. I want you to know what you just proved. There is enough evidence to support the claim that the mean level of soda is greater than 12 ounces. So what this guy did, or what you did if this is your job, you went in, you collected 39 cans, you sampled them, you did all your statistics correctly, you came down here, you go, hey boss, we're giving way too much soda, we need to reconfigure these machines because I'm 99% sure, that's pretty sure, right? Not 50-50. I'm 99% sure that we're giving away too much soda in these cans. Lower it a little bit. Lower it by half and see if it's soda, or lower it by 1/10 of an ounce, and then redo the test and pick out another 39 cans. See if you're on the money. Does that make sense? Feel okay about this? You sure? Now I'm going to change the problem just slightly. What we're going to do is say, what if the guy had beforehand just said this? Said, well, I didn't do my sample right. I just want to know if we're either above or below. So without even doing a sample, what if we change the wording a little bit and say instead of the claim that, so this all stays the same, 39 cans, 12.11 ounces, standard deviation is 0.27 ounces. Test the claim that the mean volume of soda is not equal to 12 ounces. So we're just testing whether we're giving away too much or not enough soda. So change your problem right now is not equal to 12 ounces. And I want to see how this affects our problem. So that's our change. still with a 0.01 significance level. 0.01 significance level. You all right so far? Okay. Hey, does our claim change? The claim. The claim is the volume of soda is not equal to. Does this mean not equal to? Oh, we're going to have to change that then. What's that? How do we write that then?
Equal with a dash.
So, not equal to. What's the opposite of not equal to? Well, that's kind of easy. Equal to. That's kind of nice. Is this still our h sub 0?
Yes.
Sure. Is this one still our h sub 1? Okay. Hopefully you didn't erase the last problem, right? You're just adding on to that, right? Okay, good. I hope not. So our h sub 0 is still mu equals 12, but this one, we're noticing that, well, there's no longer that symbol. Now instead of that, we have a that. Does that change anything in the future of our problem? That changes the type of test we're doing. Instead of a one-tail, a right-tail test, we're now going to have a two-tail test. So the not equal sign is going to split, and here's what that does. It splits up your significance into two different areas, right? Saying now you have to be further away to prove this null hypothesis wrong. We're going to see how that affects us. Okay, is our significance level still 0.01?
Yes.
Is our test statistic still 2.544?
Yes.
None of that changes. Yeah, the only thing that really changes here is our claim and opposite, so our null and alternative, but that's going to change our picture dramatically. So when we take a look at our picture again, in step number 5, I'm getting pretty good at that. Are you guys getting pretty good at that? Drawing that nice little, again, knock that out of the park. Oh yeah. So we got this picture again, but here our alternative hypothesis says, well, no, we're not just a one-tail test anymore. We're not just a right-tail test. We've got a two-tail test. Can you tell me, if this is a two-tail test and our significance level is 0.01, is this area 0.01?
No.
How much is that area? Ooh, how'd you get that? Because what we know is that this is alpha over 2. That's 0.005. 0.005 over there. And that means that on this side we also have 0.005. You okay with that so far? Now go back to your table for me, all right? Our degrees of freedom is still 38, so we're still down there at the 38 row. But I want you to look at that. I want you to look at the area in two tails, right? So it says area in two tails. You know, maybe I won't. If you do area in two tails, I wonder if that's even to catch that. Hopefully you guys can see that. If you do area in two tails, how much area is combined in the two tails? So that's what you're looking at. Look above that. Right above that, it says area in one tail. How much is the area in each one of those tails? So it does make sense there, right? The 0.01, that's if you look at both tails combined. 0.005 says, oh, that's the area in each of my tails. Do you understand how to read the table correctly? Okay, so unlike chapter 7 where we just always use one of those, now it kind of switches depending on whether you have a left tail or right tail or a two-tail test. You got me? So we're going to follow that all the way down. We should be on this far left column, the 0.01 that's in two tails combined, or the 0.005 that's in each of our tails, all the way down to the 38th. And we get, what'd you get?
2.712.
2.7. Were you able to find the 2.712? Again, that's a critical value. What's this? Yeah, it's symmetrical. That makes it kind of nice, doesn't it? Hey, would you tell me which one of these three regions is the fail to reject region? Or which are the fail to reject regions if you think there's two of them? Is this a fail to reject region? This would be saying it's way smaller than normal. And we're 99% sure on that. Is this the fail to reject region? Yes, this is saying it's not far enough away for me to be 99% sure that my claim is wrong. All right? or I'm sorry, that my null hypothesis is wrong. So basically, I'm not sure enough if my claim is true. In our case, since it's stated as alternative. So that's the fail to reject. This one's clearly a rejection region also, saying I'm giving away too much soda. So this is, I'm giving away too little soda, and I'm 99% sure of that. This is, I don't know whether I'm giving away too much soda or whether I'm running out of money. There's no way to tell that. This is, I'm giving away too much soda, and I'm 99% sure on that. Does that make sense to you? So that's what you do if you split up those tails. You're splitting up your significance to, it could be lower, it could be higher. That's the idea here. So question, are we still going to reject the null hypothesis? Did our test statistic change?
Yeah.
Really?
Oh, no. No, it didn't.
Did our critical values change? Absolutely. Because you're talking about two-tailed tests. You're splitting the significance amongst, or alpha amongst two tails. So are we going to still, like we did last time, reject the null hypothesis?
No.
Where's 2.54? Is it in the reject region or fail to reject region? Yeah, it's right here. That's in the fail to reject region. So we got to change this. We're not going to reject the null hypothesis anymore. We're going to fail to reject it. What's that mean? Okay, so it says we failed to reject the null. We failed to reject this. We failed to reject that the mean equals 12. Does that mean that the mean does equal 12? You don't know. It doesn't prove it right, but it definitely doesn't prove it wrong. Does that make sense? So we're not sure. We don't know if we're giving away exactly 12 or if it is more or less than, because we can't say either way that this was conclusive. We don't know for sure we're giving away too much, even though it says 12.11 compared to 12. We don't know for sure because it's not significant enough. That's what happens when you do a two-tailed test rather than a one-tailed test. Did you guys see the difference between these examples? So it really does depend on what type of test you're using, doesn't it? It's kind of interesting how we can change our decision based on what our starting information is. So how would you augment this? There's only one extra word that you got to put up there. Because either way you look at it, there's not enough evidence to say anything. You can't support your claim. You can't support the opposite of that claim. That's it. Would you raise your hand if you feel okay about our hypothesis testing?